Hey, welcome back. This is Module 2, Episode 1 of my Performance Engineering series. In Module 1, we covered availability calculations, the 4 types, how to compute them, and how OBE, the overall battery effectiveness, pulls them all together. Now that we have some performance KPIs as a reference point for assessing the performance of a BESS, it's time to talk about how we improve its performance with performance engineering. Module 2 is all about performance engineering. So what is performance engineering? Well, performance engineering is the discipline of getting or exceeding the expected performance out of an asset. And it's really it. You're optimizing the output, you're optimizing the cost of ownership, you're optimizing the return. And the asset could be a production equipment, a manufacturing process, a workflow, whole power plants. The discipline is the same. And there is why it matters. An asset that's just left to run with no oversight will typically lose between 5 and 20% of its potential performance. Doesn't matter how well it was designed. And that 5 to 20% gap is what performance engineering closes. The economics are pretty simple. If you could recover just 1 or 2% of performance on a utility scale BESS, it usually pays back the entire performance engineering program. The tools, the resource, everything. We'll come back to the actual numbers near the end of the episode. So why does BESS needs performance engineering? Well, performance engineering isn't new. It's been existing across many industries where assets are expensive and operationally complex. In manufacturing, they call it process engineering. It's the same discipline, it's just a different name. In thermal power plant, gas turbine, nuclear, combined cycle, there is performance engineers, and it's quite mature there. What's interesting is that this discipline is just emerging in renewable energy. I guess solar didn't really need it, and typically the gap between the design and the realized performance is pretty small. But with BESS is a different ballgame. In BESS, there's like battery state of charge imbalance, you got power distribution error, you got telemetry issues, and just to name a few. And all those are affecting the realized performance of your plants. The gap between design and the reality is quite wide, actually. It's that 5 to 20%. And I think that's been well documented and well discussed in the industry. And this is kind of why I'm doing this video series, is like, I believe that the discipline of performance engineering is the key to close this performance gap. How do you get started with performance engineering? Well, first you have to recognize that this is a discipline worth resourcing. That sounds obvious, but a lot of operators are still treating performance as something that's just happens when there's a problem. And maybe you review it once a quarter, and look at the financial numbers, but it's not necessarily a very robust function in IPPs and kind of asset owners. And it needs dedicated people and dedicated tools and platforms. The minimum bar is one performance engineer and a bit of CapEx for platform and tooling. You get a few dashboards, you get a little project management system, and then you could get going pretty quick. There's always going to be the build versus buy question. You can build the whole thing internally. That gives you long-term ownership and deep kind of knowledge of your fleet. Or you can contract it out as a service, but you can't just bring a bunch of SaaS tools and call it a day. There's no single right answer. It depends really on your fleet size and how much you want to invest in building the team, or how big is your portfolio. So there's 4 pillars of performance engineering, and then we will go through videos for each of them. Pillar number 1 is mapping the expected performance of the assets, mapping all the interactions between different kind of part of the assets and counterparties. Number 2 will be discussions about the platform and tools that you need to be able to perform this performance engineering work. And pillar number 3 would be the processes, like kind of the discipline you need to have, the steps and how you organize this discipline. It's a bit like project management. And number 4 would be the automation, maybe the integration of AI agents. How do you scale, manage more assets with like kind of the same team, or like just make it manageable? So we'll do a video for each of these pillars, but we're going to just do a quick like kind of chat about each of them. So pillar number 1 is really this mapping. Before you start optimizing the performance of anything, you need to have expectations on how it should be perform. And then you need to understand all the inputs and outputs. So really the interaction between different things. And as you can see, like there is many things affecting a battery asset. There is the equipment itself, and within the equipment, there's lots of different things, the battery, the PCS, the control system. But then you got all these things externally also affecting. You got an LTSA provider, you got a trader, you got an operations center, you got operators making decisions. All this could impact the performance, the commercial performance at the end of the day. So it's not just the technical, it's also how commercially it gets traded, how efficient you are with your O&M. All this is really performance engineering. It's not just the technical performance. Technical performance is a big part of it, but the overall performance. And then you need to have expectations. So you need to be able to measure the performance. So we've talked in module 1 about the technical availability. That's a big part of it, but there will be also comparing it in the market, maybe against market benchmarks, maybe also looking at your O&M time and the downtime for O&M, how quickly you recover from outages. And there's a lot of different things that could be optimized, and you need to have these kind of key KPIs. So we'll do a separate video. There'll be our next actually video where we look at building these like matrix tree maps, looking at all the interactions between the different part of the BESS. Then once you have an understanding of this, you're going to need to have platform and tools to collect all this data, to be able to then run KPIs from them, explore the data, monitor it daily, and then you're going to need ways to then track things. You're going to find anomalies, you're going to find underperformance, you're going to want to track them over time. You're going to dispatch maybe technicians, or you're going to ask OEMs to study problems. And so you need a project management type platform. So the tools and the platforms, this is the second pillar of performance engineering. That's after you get an understanding of what you expect and what all the interactions are, you're going to need to build this. Then once you have the platform and tools, then you're going to have to have a process on how you do this. And we have at Libra Energy a 4-step process that we kind of try to simplify the whole operation of performance engineering to these kind of steps, where a big part is observations. This could be someone has observed, you're doing a daily check, you observe something, you were not meeting set point, or one battery is running hotter than another, or there's something, it looks like the power balancing is not right. You need a way to record it. So being able to record observations, it's super important. These observations could be alarms that are triggered by your data platform. This observation could be like a daily report that's sent to you with some KPIs. So those like kind of layer of things that you collect. And then from this, you're going to be deriving some action items. So you're going to want to like sort this from all this observation. Is it just like you actually create a work order, someone has to go fix it, or you're going to keep tracking it, and then maybe it becomes a root cause analysis, or maybe it's an RFI. You still don't know exactly what it is. You want to ask more questions. So there may be an RFI, a request for information, that's sent to a certain party. But everything should kind of flow through the observation into action items. And then if these things can't really be actioned right away because they're too big of a problem, it's a bigger kind of action. Is maybe a study that requires multiple party to be involved to solve and resolve. You create an RCA, a root cause analysis. The goal is really the only way to improve the performance of the site is the outcomes of root cause analysis. And a lot of things could trigger root cause analysis. Maybe you had a process problem. Maybe there was miscommunication between different parties, caused some downtime, caused some missed kind of opportunity in the market. That's the observation. The action item is maybe there's no direct action. Maybe you need to do an RCA to really figure out what caused it. And then maybe you need to put processes in place. Maybe you need a better CMMS system or some automation. The RCA process will come up with like all these ways to mitigate, and then you implement these things, and then the problem should be gone. So you want to do this. You don't want to just firefight with, you have an observation, you have an action, go fix it, and then you got another observation, go fix it. That's not what performance engineering is all about. You want to track those and go fix them right away, but then like noticing that there's so many problem with a certain thing needs to trigger a root cause analysis. If it's super obvious that you need to just put a process in place, then it's just an action item, go put a process in place. But it shows really the importance of the processes and having this kind of project management platform and tools in place. Then the last pillar is automation. So this works well for 1-2 projects, maybe you have 5 projects, maybe a couple performance engineers on the platform, and you can manage like 5 to 10 projects, no problem. But as you grow and every BESS owner is growing, the market is kind of on the upswing. So you're going to have to automate. And that's going to be a very key part of the strategy is the platform, the team, everything needs to be built in a way that you can automate the detection of the problems, so creating the observations, automate the reporting so that maybe your daily reports, things that kind of boil down the problems to a certain type of issues. Maybe having the automation go figure out if you're already tracking it, if there's already RCAs. And that's what really AI agents come into play is like you could easily have, if you have automation to create the observations, you could have AI agents looking at all these observations, looking at what the current actions items are, what current RCAs are, making sure that things keep moving. And then if there is a bunch of new observations, categorize them, raise them to a performance engineer that can decide if this needs to become a RCA or an action item. Automation will be our last video in this series where we're going to really look at ways to automate. It's not all about AI agents. It's also plain old kind of automation of various things, but you first need to do it yourself as a performance engineer, put the processes in place, and when all that is working well, then you can automate it. So this is just a way to illustrate the economics of running a performance engineering function in your company. And to visualize this, we're going to use a 500 megawatt portfolio. It could be multiple site, but it's 500 megawatts, either in KAISO or ERCOT. And the rough numbers came from Modo Energy benchmarks. Today, I think this is 2026. Looks like the economics of a plant in KAISO in the market and ERCOT are pretty much the same. Around $30,000 per megawatt per year. And then you could plug in your numbers if you know what your assets do, but those I think are quite average numbers. So if you add a 500 megawatt portfolio, that will return 15 million of revenue per year. So 1% of this is 150,000. So we know we have maybe 5 to 20% of things to recover. An asset that performs quite okay, maybe there's only 5%. Maybe putting performance engineering should at least recover 2 or 3% out of this, get the asset to perform to 98, 99% of its potential. It's hard to tell. Every asset's a bit different, but you can here do the math very quickly. I think if you get 1 or 2%, you can easily have payback. Assuming that maybe the platform is a bit of a capex that you're going to depreciate over a few years, then it's really your labor, your performance engineer, regardless of if you have a SaaS platform, some advanced analytics tools or whatever, you're going to need a performance engineer to do all this. So that's probably your main cost. A bit of a capex depreciation or service. With a couple % of improvement, you'll easily break even. And after that, everything is profits. So use this slide to maybe do your own math and to justify internally building a performance engineering discipline. So what's next? We'll start with pillar 2, the mapping, and then we'll do the platform and tools. So then we know what to do, we have the tools, and then we'll talk about the processes. And this is where you could really get started with your team, start following the process, and then we'll talk about automation. So we'll see you in the next video. We'll talk about expectation mapping, interaction mapping.